this idea of accelerated solar evolution, stellar evolution, is interesting to consider when we look at our own solar system. It was mentioned before that stars eventually would begin to pop like popcorn if you go back early enough, because the amount of mass necessary to form a star would be dramatically reduced. Say, for example, if the effect of gravity was 100 times what it is right now. So stars would be much smaller, evolve very much quickly, and it was proposed that this helps explain the energy output we see from quasars. Well, it's interesting to consider this model when you look at our own galaxy, own solar system. This explosive era within our own solar system, I think is pretty conclusive. Now, there is a physicist named O.K. Manuel, and he had the opportunity to look at some of the first soil samples from the moon. And one of the things that he noticed, and he also got opportunities of looking at other material from across the solar system. What he observed is there's this element called strange xenon. It's an isotope, a radioactive isotope of xenon, an inert gas. But the only way you could produce this isotope of xenon is from a star that has exploded. Well, he presented a paper at the American Astronomical Society, and he said, I think our sun blew up. And he came up with a model. And I had an opportunity to listen to some of the people's comments about this, and they kind of it was so far outside the box that he wasn't taken very seriously, because if a star blows up, and as we would assume and using the model, there's very little left behind. If we look off into space, we can see nebula that have been cast off into space from when a star of any size explodes. There's nothing left. There's no planets. Everything is vaporized except for maybe a white dwarf or some small remnant core within the center of this, what was once a solar system, perhaps. So his proposal and his solutions just seemed kind of ludicrous, and his work has primarily been ignored. Well, the proposed model, this kind of accelerated stellar development, astrophysics, the accelerated evolution of stars, it very much is likely that our sun or our proto-sun actually blew up. And I think the following is there's pretty good evidence. Besides this evidence of strange xenon, you have what I would call the angular momentum problem of our solar system. And what this is when we look at the development of our solar system, it's believed we came from a nebular cloud of debris, small objects, and it all collected in a large cloud. And through gravitational collapse, it would collapse in one dimension, and if it has a rotation, it would all collapse into kind of a cloud-like disk. Now, within this disk, there would be no region that's faster than any other. If it was moving faster, it would bump into all the other material, or all the other molecules or in clumps of matter that were there, and this momentum would be evenly distributed. So there would be no one large place going much faster than any surrounding neighboring particles. This large, evenly rotating kind of collection of matter, dust cloud. And over the course of time, this matter would slowly compress back in. This is the standard model for the evolution of our solar system. And most of the matter would fall within the sun. Well, similarly, since all the matter, as the matter comes compressing in, it carries with it the angular momentum. And just as, say, a skater standing on a skate, when they bring in their arms, they spin very quickly. Well, you would expect the angular momentum to also be carried into the sun. So the sun has way more than 99% of all the mass, yet it doesn't have 99% of the angular momentum. Somehow, the angular momentum was distributed back outwards, and most of the angular momentum of our solar system is contained within Jupiter. How did this happen? Well, if a proto-sun exploded, it would spread back out that angular momentum that was garnered originally in the sun, and the outer perimeter would be most carried outward. That was carry most of the angular momentum, and it'd be spread out and redistributed back within the solar system again. Now, this also explains why our 4 inner planets are rocky as opposed to gaseous. Now, when I was a kid, it was proposed that the 4 inner planets were not like Jupiter or Saturn or Uranus or Neptune, these large gaseous planets, was because as the sun formed, its radiant energy would push off these lighter molecules of hydrogen and helium and not allow them to coalesce or be gravitationally drawn to the inner planets. Well, this was fine until we started looking at distant solar systems, and we began to see stars with planets larger than Jupiter within an orbit less than the orbit of Mercury is right now. We find many of these large gaseous planets very close to their mother star. So this presented a problem. How did these stars form? So we begin to see another after-the-fact solution. Well, what must be happening is that maybe these planets are kind of slowly marching their way in. And then, but it still leaves that, well, why do we have our gas, there's all these after the fact, and it doesn't fit with observation. But if there was an explosion, it would rip all the atmosphere off the inner planets, then it would come crashing back in and recoalescing around the outer planets, and explains quite nicely, I think, why the angular momentum is distributed and why the inner planets are not gaseous, yet whereas the other planets we see, there's evidence of many more planets that are close to their mother star that do have these large Jupiter-sized masses of atmospheres. The other thing, this explosive era, you have Uranus, where its angular rotation has been flipped around. Something big and powerful hit it when it was forming and flipped it around. You have Bode's law, with basically if you double the distance each one of the planets, there's this nice kind of rhythmic pattern, except when we get to where the asteroid belt is, and, well, it's kind of, maybe there was something there, but there's nowhere near enough mass to keep that pattern going, Bode-Titus law. And, well, one of the reasons that relationship was dismissed is the amount of mass we see in the asteroid belt series, and it just isn't enough mass to even come close to a planet. Well, if you go back in the early evolution, well, everything was smaller. Plants were still forming. The star was much smaller. Everything was much smaller. So the explosion and the event and what was destroyed would have been much smaller. So that whole dismissal of that relationship, just because the amount of mass doesn't fit with a typical planet, is moot. It just records the size at that time. You also have the very fact of the formation of our Earth-Moon relationship. The Moon is supposedly derived from a Mars-sized object hitting our Earth and destroying everything and recoalescing the two objects. And the evidence of this is pretty conclusive. Where did all this explosive energy come from so late in the development? And right now, by that time, there was planets starting to form, there was moons. Somewhere there had to be something that would cause this vast disruptive influence of where planets are flipped over on end, and Venus gets spun in another direction. All the atmospheres get blown out. We have this period of late bombardment of asteroids. If we spend all this debris outward, eventually this debris will come back kind of in a cyclic kind of a pattern. And so normally you would think, well, geez, in a nebular cloud, all those vast variations of motion of any sort of matter should have long been resolved. Yet we see all these asteroids. We look at the surface of the moon and we can see something very late in the development caused all these asteroids to be coming in. Where did they come from? If there's an explosive error to our solar system, when it got fairly well developed, this would explain it. All the pieces of puzzle kind of make sense. Thank you for your time. I look forward to sharing more videos. I think it's getting now time probably to work on some of the mathematical development of it. Thank you very much Thank you for your time, and I look forward to sharing more of the model. Thank you.